Welcome to a brand new explainer. Today, we're going to totally demystify statistics and uncover the incredibly powerful stories that are hidden right in front of us, buried inside of numbers. We're bombarded with data every single day, from opinion polls to average rainfall to the median price of a house. But how do we actually make sense of it all? Well, that is exactly what we're going to unpack today.
Okay, let's dive into this. I want to challenge a pretty common assumption right out of the gate. Is doing statistics the exact same thing as doing mathematics? The short answer? No way. Imagine you're timing two runners, let's call them Susie and Tanisha, over 7 different races. If you simply multiply or add their race times together, well, you're doing math. But if you analyze the spread of those times to see who's the more consistent runner or who's most likely to win the very next race, now you're doing statistics. Why? Because in statistics, the context of the numbers matters entirely.
Absolutely love this quote from Richard Schaffer, the past president of the American Statistics Association. He says, "Statistics is about numbers, but numbers in context. These are called data." Read that again, numbers in context. That real-world context is exactly what gives numbers their shape, their variation, and their ultimate meaning. It's not just about crunching numbers, It's about understanding the world around us.
So, here is our roadmap to get us to that understanding. We'll start with math versus statistics, then walk through the 4-step process, compare categorical and numerical data, look at analyzing with graphs, identify some common graphing pitfalls, and finally, we'll interpret our results.
All right, part 1, math versus statistics, setting the foundation. We touched on this in our hook, but let's make it crystal clear. Mathematics is all about operations, generalizations, and abstractions. Statistics, on the other hand, is a completely different ballgame. It focuses on variables, distributions, and variation. So the absolutely crucial takeaway here is that statistical reasoning relies entirely on the real-world context of the numbers being measured. A pure number, that's math. A number with a real-world story, that's data.
Moving on to part 2. The 4-step process, or basically how we actually do statistics.
And this brilliantly illustrates the complete journey of data. You don't just jump straight into making a graph. Actually, scratch that. A lot of people do, but you shouldn't. Doing statistics is a deliberate 4-step sequential process. Step 1, formulating questions. You have to ask something that actually has variability. Step 2, collecting data, getting the actual information to answer that question. Step 3, analyzing data. This is where you choose the right visual representation, like a graph. And finally, step 4, interpreting results, using those representations to answer your original question.
Part 3, categorical versus numerical data, knowing exactly what to gather.
So, the specific questions we formulate in step 1 completely dictate the type of data we have to collect in step 2, and it generally falls into one of 2 buckets, categorical or numerical. Categorical data is information grouped by labels. There's no specific mathematical order to it. Think of favorite vacation sites, the types of cars parked outside, or favorite colors. Numerical data, by contrast, is measured on a continuous scale and is ordered numerically. For example, if you're measuring the lengths of insects, like finding out that the largest cockroach is 8.3 centimeters long, which is honestly just horrifying, by the way, you're dealing with numerical data. You can't put colors on a continuous number line, but you certainly can with insect lengths.
All right, part 4. Analyzing with graphs. This is where we tell the story. The type of data you have dictates the exact graph you should use. Here we have a bar graph showing 3rd grade favorite colors. Bar graphs are absolutely excellent for categorical data. The discrete, separate bars show quantities that you can really easily compare side by side. And since yellow and blue don't have a numerical sequence, the bars can technically be arranged in any order, and the graph still perfectly communicates the quantities.
Now, what's really interesting about this slide is how circle graphs or pie charts function. They show ratios of a part to a whole. This donut chart here shows the number of siblings in a family. Because circle-style graphs display proportions or percentages rather than just raw quantities, they make it incredibly easy to compare wildly different sample sizes. You could easily compare this data from a single 30-person classroom to the data of an entire 400-person school, all because the percentages give you a perfect proportional snapshot.
So let's see how this builds when we tackle numerical data. That's where we use continuous data graphs, and the differences here are super vital. A line plot is essentially a count of things along a numeric scale. You draw a number line and put an X above a number for every single data point, kind of like tracking quiz scores. Every piece of data is visible. A line graph, however, connects plotted points with a line to show continuous change of related data over time. Think of measuring the length of a flagpole's shadow throughout the day. Because time is continuous, it actually makes sense to connect the dots.
Next up, part 5, graphing pitfalls.
the speed bumps of data analysis.
As helpful as graphs are, man, they can also be incredibly misleading. There are specific graphing pitfalls you really need to watch out for. First, not using 0 as the origin on your axes. That can severely distort the visual proportion of the data, making tiny differences look absolutely massive. Second, confusing the graph scale. And third, using a line graph for discrete categorical data. I mean, think about it. Drawing a line connecting red, blue, and green favorite colors implies a continuous relationship between completely unrelated labels. It makes absolutely no logical sense.
Let's actually look a bit closer at that second pitfall, confusing the scale. Check out this confusing pictograph. The key clearly says each animal picture equals 50 people. But whoever made this graph drew the dog incredibly large and the cat very small. If you just glance at the symbol size, you'd think dogs were overwhelmingly more popular, even if the actual count of the symbols is the exact same. Always, always check the key, and do not let visual scaling trick you.
Finally, Part 6, Interpreting Results, Finding the Actual Meaning.
We finally arrived at the last stop of our data journey, interpreting the results. A researcher named Curcio defined 3 distinct levels of data comprehension. Level 1 is just reading the data, answering literal facts like which is most. But true statistical literacy requires us to go a lot deeper. Level 2 is reading between the data, finding relationships and comparing clusters. And Level 3, that's reading beyond the data, making inferences. It's asking, what does this graph not tell us? Or would the results change if we asked a totally different group of people? This requires critically evaluating the information you're given.
Which brings us to our final thought. The next time you see a flashy statistic on the news, in an advertisement, or maybe in a political poll, I want you to stop and ask yourself, how will you read beyond the data? What context is missing here? What story is the graph actually trying to tell you? And more importantly, is it a true one? Data literacy isn't just for math class, you guys. It is an absolute necessity for navigating the real world. Keep questioning, keep learning, and I'll catch you in the next explainer.